Okay, I'm going to explain my topic is RISC-V core implementation on FPGAs via machine learning based hardware Trojan. This presentation about machine learning based strategy for detection classification of HT FPGAs immediately on RISC-V core. We'll give some basic introduction of FPGA. Security of FPGA based system, implementing and model data collection, extracting the data from the FPGA bitstream, generating the data sets, training and testing sets, model performance, hardware Trojan, attack model and HT in FPGA designs. And the final one is Trojan taxonomy. We'll give some basic introduction. In the modern global economy, uh, where we smart electronic products like commercial CPUs are frequently built by humans. The prospect of malicious modification in integrated circuits is very relevant, produced and distributed throughout several nations by several business. CAD tools are used throughout their design cycle. A malicious hardware modification known as hardware Trojan may proceed through various phases since numerous parties can be exceed the production flow. ML algorithms provide a data driven solution to this issue because algorithms and computational capabilities drive them. ML models can improve our capacity to identify hidden threats by examining integrating patterns and anomalies in the behavior of integrated circuits. HD detection and classification has follows. In HD detection, a systematic methodology for an extensive collection and estimation of numerical data from FPGA bitstreams. Our proposed approaches includes the extraction of valuable insights from the soft RISC-V microprocessor spanning various data sources including hardware performance counters and extending to more complex to acquire metrics such as instance design clock frequency and power consumption. And the second point, comprehensive feature evaluation. We extensively explored the importance of features in ML based HD detection and classification. Our experiments suggest that feature derived from the synthesis and implementation process play a critical role in achieving high model performance. Data collection. In this data collection, define, train, and evaluate the ML-based models for classifying the HTs. On the left side of figure, we report the FPGA related flow, which aims to extract and gather relevant features from the RISC-V bitstream. Our feature extraction process started with implementing the RTL design of a soft three-stage pipeline RISC-V IBEX processor, which was further modified to include one of our four potential HT models described in Trust Hub. In our detection and classification modeling, we categorized HTs as either triggered or non-triggered expectation, the critical HT which operates continuously, and subsequently categorized the first group of features as performance features like PF and second group has implementation features IFs. Our data collection process resulted in 160 data samples, four distinct HT types with triggering and non-triggering conditions, and an HT scenario. The next slide is dataset generation. In this dataset generation, this process involves sampling a subset of training data and training separate models on these subsets. Through this investigation, we better understand the model's robustness and ability to maintain accuracy scores. Generalized to new data under data scarcity, providing valuable information for practical development scenarios. Data collection is done either after a selected HT has been turned on, triggered, or when left inactive, non-triggered. Critical trojans cannot be turned off. Random split between train and test set serving has performance baseline. By including both triggered and non-triggered HTs in the initial, we provide a more realistic view of the real data distribution. Data evaluation. In this data evaluation, first we discussed about cleaned and split data sets. In this cleaned and split data sets, we have two types of sets: trained data set, test data sets. In trained data sets, it is XGBoost model, and second one is test data sets has model performance and sources. Extracting the data from the FPGA bitstream, said to be bitstream, that is data collection estimation by enabling the insights hardware performer counters like design, clock frequency, and power consumption. Basic essential information is lookup tables, flip-flops, and timing characteristics. An estimate of their number can be extracted through reverse engineering of the circuit logic netlist, switching activity interchange format. In this model performance, the input feature impact the model performance in the validation strategy. The selection of XG boost our machine learning framework, a state-of-the-art model recognized for its effectiveness in handling tabular data with relatively limited sample sizes. We discussed about the model performance. Second point is by evaluating the model performance across several floods or data set subsets. Cross validation increases our confidence in the model performance. This Letizius validation process gives us a reliable evaluation of the model's capabilities by enabling us to guess how well it generalizes to previously unseen data. How does the input feature influence the functionality of our model? We explored three distinct scenarios. Both PFs and IFs are inputs to configuration. We leverage both performance and implementation features as inputs to the model. Effects of hardware Trojan. In these effects of hardware Trojan, three types of hardware Trojans: change of functionality. HD alerts the functionality of a circuit. Examples like Daniel of service bypassing of encryption algorithms. And second point is degradation of performance. IC fails or damages the performance, which could potentially the critical system. And the third point is leakage information. Trojans may also directly leak and sensitive and data handle the IC or compromise the security offered by cryptography algorithms. This might entail disclosing sensitive data such as cryptographic keys, side channels, delay, power, etc. Attack models. In adversarial model list that demonstrate the precise times, locations, and methods by which a Trojan can be introduced into an IC founders, SoC integrators, and 3PIP vendors are the exclusive source of Trojans. One or more of these entities can insert a Trojan in the following such ways: Model A, Model B, Model C, Model D, and Model E. The final one, Model F, Model G. Hardware Trojans may be third-party intellectual property that a design house or SoC developer purchases. In the current landscape of semiconductor design, where SoCs are created by integrating multiple 3PIPs to lower complexity, lower cost, and accelerate time to market, this poses a serious threat. See in FPGA design, hardware trojans in FPGAs may exhibit triggered or always on activation characteristics. However, the ability be IP dependent or independent is a special feature of hardware trojans. In hardware trojans based on FPGA devices, trojans based on FPGA devices can also have unusually harmful effects, like causing the FPGA's resources to malfunction or leaking the IP loaded onto FPGA. The second point is activation characteristics. IP dependent Trojans, IP independent Trojans. Payload characteristics, malfunction, IP leakage. HT taxonomy. This HT taxonomy, insertion phase, abstraction level, activation mechanism, affect location, physical characteristics. Actually, you have given the some sections, so I can prepare those sections. I am discussing about the HT taxonomy. Uh, I'm going to explain insertion phase. In this insertion phase, the design flow consists of several phases, from determining design specification to its assembly and packaging. To due to globalization, circuit tampering can occur at different stages. For example, like Trojan can be realized by adding some extra gates to circuit netlist at the design phase or changing its mask during the fabrication step. Like specification, design, fabrication, testing, assemble, and package. And second one is abstraction level. In this abstraction level, the level of abstraction determines the control and flexibility and may have a Trojan implementation. At the system level, a circuit is defined in terms of modules and interconnections between them, limiting an adversary to the modules interface and their interaction. On the other hand, all circuit components, their dimensions and locations are determining. At the physical level, a Trojan can be inserted in the white dead space of circuit layout with the least impact on circuit characteristics. And, and activation mechanism. In activation mechanism, Trojans may always function or they can be conditionally activated. Always on Trojan starts as soon as their host design or powered on, while conditional Trojans seek specific internal or external triggers to launch an effect. In effect, Trojans can be characterized based on their effects. They may change a circuit's functionality, for example, by modifying the data path of processor. Trojans can also reduce a circuit performance or degrade its reliability by changing its physical parameters. Location. In every part of circuit can potentially be subjected to Trojan insertion. A Trojan can be disturbed over several regions or focused in one region. A Trojan can tamper with a processor to manipulate its controller or data path units. For example, on a printed circuit board like PCB, including several chips and inserts in a different benchmark with a Trojan benchmark labeled. Physical characteristics. In physical characteristics, Trojans can alert to circuit physical characteristics and assault that has many hardware manipulations. A Trojan can be functional or parametric type. Functional Trojans are realized by the addition or detection of transistors, gates, and parametric Trojans by modification to wire thickness or any other circuit parameters. Trojan cells can be used loosely or tightly in the physical layout in white space or space created by displacing the cells of main circuit. In Trojan benchmark taxonomy, it is difficult to model to Trojan similar to faults in a circuit, although both faults and Trojans potentially. In this summary, in conclusion, our XC-Boost model only obtains 100% classification and detection accuracy scores when utilizing all input features. However, we demonstrated that when combined with a more realistic test data distribution, implementing performance PFs alone insufficient achieve high accuracy. To get around this, adding at least one IFs to PFs greatly enhances model performance. And the second summary, overall, our findings emphasize the importance of IFs and the resilience of XG Boost has a robust HT detection and classification integrated circuits. References: Benjev, Safran A. and Hurst, a tool chain for bitstream reverse engineering in 22nd International Conference on Field Programmable Logic and Applications.